So with that, I'm going to turn the floor over to my esteemed colleague, Hami Kazerooni, professor in the Mechanical Engineering Department here at Berkeley.
Thank you. 15 minutes?
Yes.
All right. Thank you so much for inviting me here. Do you guys hear me, bro? OK. I was preparing this presentation for you, and I came up to try to figure out all kinds of robots around, and I actually got a little bit disappointed because I couldn't really come up to all the robots available out there. But there are so many architectures out there. We got bipedal machines. We got now machines, four-legged machines, classical arms made by Fanuc. We got a snake. So all kinds of locomotion happens. Some of them don't even, they roll like balls, and some of them fly or fish. So there are all kinds of architectures from robotic devices. Our laboratory is dedicated to design new architectures. We're not, as a mechanical engineering department, we're coming up to new architectures of machine. And of course, science fiction writers have already done another poor job of telling what we're doing. We're working on machines that do work with people. And that's what media will tell you what it is. For example, you probably have seen Aliens, or perhaps you have seen Iron Man and all that stuff. But that is, although they're very interesting, right, very, they teach you things, what inspires me the most are not those science fiction machines. We're not trying to jump over the building. We're not trying to make machines that make you stronger or do any of those at all. Those are perhaps good for entertainment. What we are really interested in is workers all over the world, perhaps construction workers, delivery services, shipbuilding guys. We're interested with auto assembly people and airliners and all these people who maneuver all kind of manual job. They work in a very harsh environment. Sometimes it's very hot, sometimes it's really cold, and they get paid very little, and they're not even represented well. And they put their body through all kind of abuse to do this manual work, unstructured work, and it's very difficult to, at this time at least, to automate their job, right? So that is what is inspiring us. And of course, I want to talk to you a little bit about Pediatric, but before I get there, I want to give you a motivation of why we're doing pediatric robotics for a second or two. Is Department of Labor, because of what I told you about workers, it says back injuries, knee injuries, all of those are considered number 1 and 2 workplace injuries. And that, to me, is a serious problem. And in fact, it is a motivation for research work. So you can not only workers, but also perhaps practitioners, firefighters, first responders, nurses, and soldiers, in addition to workers, are the ones that they put their body in abuse to do a kind of jobs that you and I really aren't doing. And of course, if I draw a map of people, you will notice, for example, as I said before, workers down here, the difficulty of job is here, for example. Soldiers becomes even harder, requires more agility. You can define that in terms of strength and in terms of endurance and agility, which manifests to bandwidth. And of course, nurses, which is amazing that I didn't know until like about a year ago, that they have a high rate of injuries, right? We can continue, and you can make that chart even better. And I'm sure everyone can come up to all kinds of people here. That is the map of bionics. These are people who need devices. And of course, if I show you about people who, on the far left of a spectrum, that they basically have almost no mobility or little mobility, are victims of all kinds of conflicts, which are mostly children, and of course, elderly. So that's the map that I have at this time. So in fact, we can actually show that the degree of a difficulty for an elderly is the same as difficult as a soldier to move, or perhaps as a worker to move around objects. These are relative. But that shows the market size or where we are. We're trying to cover as much as we can in this. So this is definitely not presenting our motivation. And I've been always asked, have you seen moving Iron Man? And well, yeah, but that really is not an issue for myself and my students. These are the guys who are inspiring us, and we try to make a difference in their lifestyles, not only through university, but also through a couple of startups that we started throughout the last 10 years at university. With all respect, all of these people are quite underrepresented when we call that economically inspired robotics, as opposed to any other nomenclature, mostly because they can't afford having very expensive robotic devices, right? And that makes the technology of making economically inspired robotics extremely challenging, because you need to create a function out of almost nothing, because you have to bring the costs down. Like adding sensors, adding computers, everything adding is actually easy. Creating function of minimal is very difficult. And of course, it opens new basic fundamentals. And it also reaches people faster because it's accessible. I already have that experience before. We started a company in 2005. It's called Exoskeleton. Our devices are $200,000 roughly a piece, and that's quite expensive for only a few rehab centers can actually have that. To give you an example, and to reach to pediatric robotics, I want to give you a foundation of what we already have. We started a trunk support exoskeleton as an extremely low-cost device that does one thing, and that basically reduces the risk of injuries in the back, right? So you can see the force without the device is this, but once you wear this device, which has basically a vest and also a thigh brace, once you bend it, it's clever enough to impose a force on your L5 span bag, so the force has become less. And that's exactly goes to the core of the problem of Department of Labor. It's not a fancy robotic device. It's not a Superman. It's not an Iron Man. None of those. It won't jump. It won't run. None of those. It reduces the force. That's exactly what the complaint we get from the workers. Experiment shows we have done that up to 60%. And here's an example of this device. It probably can be produced. The actuators are on the side, on both sides. And this is the job is being done in FedEx, in construction sites, in material handling industries, in UPS, FedEx, you name it, they do all that stuff. This is a real evaluation in Seattle. This is another evaluation of the same technology in Japan. As you see, this is a construction site, and these guys are in a very, very wrong posture for a long time until somebody else comes up and secure this beam to welding it. That's another job that they complain about having back injuries. That's very high risk. This is another one right here in California. It's the person who's doing grinding a very large ship components, and you can see the posture. This is under the hull of a ship. It's vacuuming the dust after sandblasting. And this one, I guess I can't get it, but this is showing airports in Narita Airport. We did similar technology for knees now. Knees have the same problems than back. And most workers squat. You can probably have seen them. They squat long the time, and they work on the floor or pick up things. Again, considered as very high-risk jobs among people. These are the tasks that you probably have seen. Basically, eventually manifest to deterioration of the knee. We have another device, very low cost, leg support exo, and the entire emphasis was to make this machine low cost. There is no other specification. Of course, only one thing too, technically, is to minimize the forces at the knee, but we have to make sure that this is really done with minimal amount of cost to the user. Almost $3,000, which is in robotics technology, it's very little. So that cost us almost 5 years, and we're still not done with this thing yet. Here's an example of this Japanese workers. You can see he's actually squatting, and then he can walk around with it very comfortably, and he can actually be in that position for a long time. You know, squatting is actually a form of exercise. As you know, you stand like this for a long time. With this, I'm able to actually sit probably about 15 minutes without getting tired. And once you put them together, you get a complete system. So you have actually, we have a hip, and we have knees. We also have shoulders, which we're not really, I don't have any pictures to show you, but you can see this man is doing grinding for the entire system. What we're talking about in human-machine system is intelligence of a human, right, and combining them with the strength and endurance with a clever machine to put it together so you come up to a device that actually helps the worker rather than replacing the worker. On a medical side, we go back here. Now we covered here. I'm not discussing these two. These are technologies we developed under Hulk. I'm coming back to elderly and disabled. We did similar technology, but this time is also modular, right? We have a powered hip, and we have a knee here, and we have the foot. The physician or the practitioner can choose different bionic module, and you can come up to an exo completely. This is being marketed in Europe right now. And you can see this gentleman is putting it one after each other on. And this is on breezeway right here. It's very small, light, 15 kilograms. It's probably the lightest exo. And of course, the good news is there is a manufacturing facility is being established to bring this out to people universally at very, very low cost. So this will probably come out on 2016. So at the end of the day, this is what we are being inspired with. And we continue the same thing now as our new research for pediatric robotics. The reason we're going through that because children who are affected by neurological conditions, and I have a list of those, they develop significant disabilities, right? And you only have very short amounts of time to train them to walk. And the best way of actually make them walk is to actually walk them. So you have 18 months to train them. In other words, walking becomes non-functional, and this usually causes that children to sit and then confined to wheelchair if we don't move too fast. So that means it's a temporal. We have 18 months pretty much. So the way to do that is actually make them walk. Any way we can make children walk with the earliest stage is an essential thing. For this reason, we are looking at exoskeleton for children. Myself and Professor Borelli, we wrote a proposal, NII to NSF, and then we recently got it. And that is about creating a low-cost exoskeleton for children that has very similar characteristics to what we have already done, right? And that means the task, it has to be a framework for rehabilitation, and also as an assist device if children cannot keep up anymore. So these two things go in parallel together. And we also need to develop controllers for preventing falls because these children walk really fast. There's a potential for falling. It's a very difficult job. We don't know how to do it yet. It is modular design. We have a great experience in modular design, very light. And we got to have two evaluations, one for safety, one for effectiveness. We haven't started the project yet. We just got funding, and we're looking for graduate students and PhD to develop economically inspired robotic devices for children with neurological disorders. And I think the same way we did other technologies to the market, within 3 years we will have that to market also. So we're looking for research assistants, engineers, postdocs, colleagues to work with us.
Thank you, Kaz. That's excellent. Super relevant to this theme of people and robots.
Yeah.
So it's very interesting. Can you say a few more words before we open up to questions? Oh, sorry, we have the mic. Thank you. About what are the kind of skills you're looking for? What kind of skill sets are you missing in the lab right now?
Well, good questions. Really, what we really need the most is being innovative. The skills can always be learned. Most graduate students have great skills here. They're cream of crops. And if you don't know a subject matter, you can always learn very quickly. To me, any subject matters you don't know, it's a matter of a few weeks to pick up. So the key issue is motivation and coming up to a technology that does not remain in the lab as a demonstration technology. That to me is the key. The moment I see the end of that would be a paper or a demonstration of a technology only, I'll shy away from it, mostly because the community is waiting. It's been so long for people with mobility disorders, things haven't been invented. Or if it has been invented, it has been in the lab. So we have a serious push to get things out with the evolution of all kind of entrepreneurial thing in Berkeley, I think it fits our character to shorten the cycle time from development to the market by far shorter than it was about a decade ago. So motivation would be my number one characteristics in the student.
So one thing, for example, I think about, you want students with really good design skills.
Yeah, I'll go through that.
Power systems.
Obviously, it has everything. Like you need to design this machine, so you really need to be creative and start understanding kinematics and dynamics of machineries. Eventually, needs control of devices. You need to know everything related to control in terms of nonlinear stuff, stability. All kind of algorithm. Eventually, when it comes to human-machine interface, we need some sort of intelligence. Right now, we have, for example, in our EXO, we have an iPad, and information comes to the iPad, and the practitioner thinks, oh, the gate I wanted is not the same gate. But I can tell, just in a matter of time, within a year or two, the iPad will tell the practitioner suggestions of how to change the gate, for example, so the guy walks symmetrically. So to me, sky is really limit here. And then we also need electrical engineer to make these software housed with minimal space, very small computers, low cost, small batteries. So we really are going to have a machine that eventually costs no more than a price of a powered wheelchair or even unpowered wheelchair to community.
Okay. I'm curious, when you say the dynamics and stability, one of the things that I'm curious, do you do a lot of simulation and modeling, or is it mostly experimentation?
No. We do all that stuff too. We can't hack that stuff. You guys know. I mean, if we wouldn't hack this, we wouldn't have a PhD student. We're not hacking. But we're not really, when it comes to presentation of 15 minutes, I'm going to skip a lot of theories here. For example, on stability, one of the problems we're having is our exos, people will fall, and they have already been hurt once, so we don't want to hurt them again. So they will fall. So we want to minimize the risk of fall, and we have some technologies with gyro things to make sure that they are being stable. And we do a lot of modeling of these devices, like similar to inverted pendulums and several degrees of freedom. We look at analysis, like how you stabilize them. And also we have to make sure you don't stabilize them too fast, because these guys can't tolerate very fast, high bandwidth motion. They get sick, actually. So there's a lot of analysis. And right now, we still do not have any hardware in terms of stability analysis, stabilizer. So we do have a lot of simulation and dynamic modeling. But at the end, we have a responsibility. We need to make a prototype that goes directly to an entity to bring it to the people.
Good. Okay.
Thank you.
Questions? In the back. Yes.
I have two questions regarding the actuators for the TS exoskeleton and the leg support exoskeleton. So how many actuators do you have for the trunk support exoskeleton?
Two.
And
two sides.
How do they work? Like when?
Well, I mean, these are cleverly provided torque for you just as a function of the posture. And number two aspects is it won't do anything else. So one of the issues about human-machine systems is not only it adds something to your functionality, but also we have to make sure anything else that you would be able to do in the past, you can still continue doing it, like climbing stairs. Like, for example, you would know this is the same as that from a standpoint of a mechanism. But mechanism has to differentiate between those two instantly, very quickly, and faithfully. Not even once had to go wrong. In fact, we have given demonstration. If the worker feels when they're coming downstairs, there's a potential that they tip over, that algorithm is out of question here. So I'll go through details of actuation with you. It's a little bit hard for me to draw pictures and things for you. But basically, it does one thing faithfully at all times, not too sophisticated.
So, Hami, because last week we heard from Claire Tomlin about safety and reachability regions, et cetera, so you can provide formal guarantees that you're staying in a safe zone. So it seems like that may, something analogous may be relevant here.
It might be. Unfortunately, I didn't. I wasn't here. But we try to embed a lot of intelligence in terms of hardware, not software. So for example, the exoskeleton on a medical device has a different knee actuation. We call them torque generators because they don't provide power. They actually absorb power. And the actuation on the hip is also different because now it generates power because it just actually goes through the swing, stance, swing, stance. We make sure it provides power at the right time and turns off at the right time. Right now, we're getting 8 hours of a battery life for a locomotion. Neither of us walks for 8 hours. And people still complain batteries are bottleneck for robotic devices. I don't think so. I think we have to be clever about how we use the power that we don't even have, right? So these questions you're asking is really valid, and these are innovation that I think may not be too academic, but eventually we'll find academic roots. Right now, it doesn't have that. But one of the issues I got to tell you, the knee actuators or torque generators for LSE has no power either, but it's got a tiny actuation that moves the device in a different control mode. Because knees don't usually use power. They actually dissipate power. So we go back to biomechanics to understand principles, and we come back to implement them in the cheapest possible way. And that makes it difficult because I actually prevent my students to have too many sensors, too many computation, too many motors. Because the moment you use that stuff, things become actually easier, but a lot of work. But in this method, we're actually making a lot of thinking, but eventually we'll do it. Thank you.
No, I'm not trying to unplug you there. Keep going. Actually, maybe Stuart will get set up, and we'll take one more question or two more quick questions. Okay, in the back.
You said the functional product is actually being sold in Europe and not in the US. Any for that?
Just because we got our money from Europeans, right, and they get the license for Europe. And we can't sell because we're confined to FDA, so we're not selling. They're selling, so we see what happens.
My question was along the lines of, you said you wanted to get this product out, especially for pediatric robotics in 3 years. But what are the hurdles, or what is the landscape like for regulation, policy, and FDA?
Yeah, those are. Yeah, it really exists. But I think I want within 3 years the life of this project, we will have prototypes that faithfully help a person at least in a laboratory environment, at least in a laboratory, and eventually in VA hospital or a children's hospital, in that level, rather than spending too much time finding basics. I think once we have a few systems out, the community is so smart that they get excited and they add more juice into it. More scientific issues will be added later on. Right now, people are in rush to have machines going on.
Well, because one thing, Hami, is that what's interesting is you mentioned learning, that the system would essentially learn from the human to essentially observing. And it seems to me that that's one of the other benefits of a system like this, because it also provides a kind of monitoring of the worker so that at the end of a day, you can see how much force, how much impact was absorbed by that person. And that would be very helpful, I think, from insurance and liability issues. They want to be able to essentially monitor. So even a passive device that would just tell you, because this is a big thing in sports right now, right? There's a big push now to instrument helmets and other things so that they can actually monitor how athletes are performing. So that, for example, head injuries and other areas can be quantified. Thank you, guys. Okay, so our next speaker is Professor Stewart Russell. He's professor in our EECS department and has been on the world stage recently for his leadership in the area of concern about autonomous weapons. So I don't know if you're going to touch on that today. No, he's going to talk more about that.
No, because I'm not building them, and stopping people from building them is not really a PhD topic in robotics.
All right, okay. But if you are curious about that part, that is going to be featured at the upcoming Citris Day, which I want to make sure everyone knows about, which is on the 13th of October. And Stuart will be giving a special invited lecture there. And there'll be a number of other talks, including a panel on Will Deep Learning Revolutionize Robotics? So stay tuned. And so information about that is on the Citris website. All right, without any further ado, Stuart.
Okay, so I should say I'm happy to take questions about autonomous weapons later. Okay, so my contact with robotics is sporadic, but it's motivated by this fairly simple fact that if you figure out how many muscles people have and how frequently, at least in theory, they could actuate them, it comes up that in your lifetime you do about 20 trillion things. And if you look at the kinds of methods, so even if you're impressed by DeepMind's deep reinforcement learning techniques, that kind of maxes out at somewhere in the high 30s or 40 steps. Deep Blue sometimes does 20 or 25 steps of look ahead. So you're not getting close to 20 trillion. And just thinking that Moore's law is going to fix that, right? Yeah, dream on. It'll get us to Deep Blue in 100 years' time. We'll be doing 35 moves of look ahead, or something like that. So, so how on earth do we do it? Well, so for a long time, I think the first paper I published was NIPS 97. We're trying to figure this out, and it's not a mystery that hierarchy has a lot to do with it, right? So if I want to go to the airport, I don't think about, okay, should I move this finger slightly that way, that finger slightly this way, this leg slightly up, that, and close this eyelid. That's not what I do to go to the airport. I think, okay, am I going to drive or take a taxi or take BOT, right? And then each of those introduces further choices. Shall I walk down to Rockridge, or shall I have someone take me to West Oakland because there are more trains, or whatever. So that this is a very old idea going back to the very beginnings of work in planning in the early 70s. And why is this going forward? Okay. So the basic view is that there are actions. The highest level action is called ACT. There are actions at different levels of granularity, and each of these high-level actions can be refined in various ways. So go to SFO can be refined by saying I walk to BOT and take BOT to SFO, or I can refine it in a different way to take a taxi and so on. So each high-level action has possible refinements, and eventually those refinements bottom out at some primitive level. Okay, and then the goal is to find a primitive action sequence that necessarily achieves the goal of the planning problem. So this is sometimes called hierarchical task network planning, or HTN planning, and it's been around for a long time. And there's this strange history to it, which is that despite the fact that it's been around for a long time, no one knows how to do it. And the symptom of this is that if you look in the literature, you will not find any description of transition models for high-level actions that makes any sense. Okay, but if you're going to do planning, then and you don't have a transition model, then you're kind of stuck. I have to. Sorry, this automated timing. I don't know who's.
Got taken over by some kind of
something came into my laptop and put that on, because I never ever have that switched on. If you can. Okay, so without a transition model, you can't, for example, come up with a provably correct high-level plan, right? But that's sort of the whole point, if you like, of hierarchical planning, is you should be able to reason at the abstract level and say, okay, this general plan, right, walk to BOT and then take BOT to SFO, that works, okay? The other plan, drive to SFO, doesn't work because, it's in the rush hour and it'll take way too long, so I'm not going to do that plan. I'm going to take the BOT plan, even though it's sort of unpleasant, especially in hot weather, to sit in the BOT train. It's still better than being stuck in traffic for 2 hours. Okay, so a human being thinking about this has no trouble deciding on a high-level plan. You can say, yes, this works. It's a lower cost plan than the other plan, and so on. We can do all our reasoning at the abstract level. So something is seriously wrong. So we tried to figure out what could be wrong. In particular, there's a property that you would like planning algorithms to have, which is called the downward refinement property. It says that if you come up with a high-level plan that claims to be a solution, then that plan needs to have a primitive refinement in the hierarchy that is, in fact, a solution to the problem. And as early as the late 80s, people had given up on achieving this downward refinement property. They said, look, this is hopeless. It just doesn't hold in general for hierarchical planning. OK. So we started thinking about this, and we realized, look, there's something fishy there. Because if you're claiming that a high-level plan achieves a goal and it doesn't have a primitive refinement, then you're telling a lie. Right? Well, how can an algorithm tell a lie? Because you're actually stating something false in your description of the high-level actions. And in fact, it's pretty obvious that if you only state true things about high-level actions, then the downward refinement property necessarily holds. Right? I don't need to tell you exactly how to write transition models for high-level actions. But if you write the truth about the high-level action, and that truth suffices to establish that the goal will be achieved, then necessarily that high-level plan has a refinement that achieves the goal. Otherwise, you've told a lie. So there has to be a solution to this problem. And Angelic Semantics is the solution that we came up with. And it's based on this idea, which is pretty familiar to some of you, I think, of a reachable set. But it's a reachable set in a certain sense. So a high-level action has a reachable set. This is the set of all possible outcomes that the action could have under any possible way of refining it down to a primitive plan. Okay? So the transition model for the high-level action is essentially what is the set of all states you could reach if you execute this high-level action under any way of doing it whatsoever. Okay? So that looks like a non-deterministic transition model. It looks like saying if you do this high-level action, one of these outcomes could occur. Right? But the key point is it's not a non-deterministic outcome in the usual sense, right? Which is that it's non-deterministic in a bad way. I don't get to control which of those outcomes happens. Therefore, I have to make my plan robust against all possible outcomes that could occur, right? That's the kind of non-determinism that we typically think of in robotics. And that's a sort of worst case or demonic non-determinism. This is the kind of non-determinism you have in the phrase NP-complete. Right? Non-deterministic polynomial time means polynomial time if these non-deterministic choices are all made in the right way. Right? So it's called angelic. In the programming language community, they talk about angelic non-determinism. And this is the right sense of non-determinism we have here, because you're going to get to choose how that abstract action gets refined. And so we only need it to be correct in the angelic sense. So for example, right, if you look at this point here. So if the reachable set of a sequence of high-level actions intersects the goal anywhere, then that means that this sequence of actions is necessarily a solution. Okay? That means it's guaranteed to have a refinement that will achieve the goal. Okay? Whereas if you took the classical notion of non-determinism, you would have to have the goal entirely within the reachable set. Right? So no matter what outcome occurs, it's going to satisfy the goal, and we don't need anything that strong. Okay? So under that semantics, everything works out. We have a formal language that allows you to concisely describe these reachable sets or upper and lower bounds on those reachable sets if the reachable set itself is too complicated to describe. Okay, so for example, if I just want to describe going to SFO, and I don't want to tell you how to go to SFO, right, then that action will always add at SFO to the outcome set, right, the outcome state. And possibly it will add that your car is going to be at SFO. Right? So this notion of a possibly add condition is a generalization of the classical way of describing actions that goes back to the Shaky project, the strips notation. So you have things like possibly adds. You can have controllable outcomes that this literal, this Boolean attribute of the outcome state is controllable. You get to choose whether it's made true or made false by your high-level action. So with that notation, we can get concise descriptions of high-level actions. And then from there, we can show that it's possible to derive algorithms that plan with these representations, and they produce guaranteed correct high-level plans. If you extend this notion with cost, you can get cost-optimal plans, both for the offline and online planning case. So just to show you some experimental results, so we have a generalization of the blocks world called the warehouse world, which is sort of actually has the world has spatial extent and X, Y, and Z locations. And so when you run either a non-hierarchical planner or a classical HTN planner, which just has the hierarchy information and uses that essentially to constrain the search space for plans, but doesn't actually have high-level annotations, it's completely unable to solve this. It's a 90-step shortest solution for this planning problem, and they're unable to solve it in several hours of runtime, whereas the hierarchical planner with the descriptions in terms of the reachable sets solves it in about 1/10 of a second. So that's fine for the classical case where actions are deterministic. We have another thread of work on hierarchical reinforcement learning for dealing with stochastic cases with unknown dynamics. This I'm going to go through the theory fairly quickly because it's a little bit fiddly. But the basic idea is actually in a theorem from Perrine Varaya in 1978. Unfortunately, we didn't know this theory. If I had just gone across the road and asked him, he would have told me, but we ended up reinventing that whole theory. So in hierarchical reinforcement learning, if you think about an MDP, and you think about trying to put some kind of hierarchy on top of that, one of the biggest problems is that as soon as you abstract the states of an MDP and then try to have a higher level MDP sort of superposed on top of that, you lose the Markov property, because the transition probabilities for an abstract state model depend on the history of where you came from, and therefore the Markov property goes away. So there was lots of work on hierarchical reinforcement learning that failed for that reason. It just doesn't work either in theory or in practice. But there's another approach, which is to talk about hierarchy purely in terms of high-level actions, which is where it connects back to the planning work. And so with a high-level action, basically you run the action until it completes without making any decisions. And then once the action finishes, you get to make another choice. Okay? And so the abstract MDP is formed from those choice points, the states where one of your high-level actions finishes executing, and then you get to choose another high-level action. And what Praveen showed was that those choice points form a semi-Markov decision process at the abstract level. It's semi-Markov because running a high-level action can take an unpredictable amount of time, depending on exactly how it pans out as you execute. And then, once you have that, then you can build still higher level actions, and you can have a whole set of layers, a pyramid of semi-Markov decision processes built on top of your primitive level. Okay. So semi-Markov means that it's Markovian in the state, but the number of time steps to execute the action is unpredictable. So a standard Markov decision process is a special case where every action takes exactly one time step. Okay. Okay. So the key idea to take away from this part is that we're expanding the state space. So this is the physical state space S, and we're expanding it with additional internal state information, which represents what you can think of as the call stack in the hierarchy. So in the hierarchy I showed you before with the airport actions, right? The call stack would be saying, okay, I decided to go to SFO. I decided to go to SFO by walking to BART and doing BART to SFO. So it would basically be the choices that you made down this hierarchy which control what you're allowed to do next. And that's the internal state of the agent at that point. And if you combine the physical state with the internal state of the agent, then what you have is a semi-Markov decision process on that extended state space. Okay. And then what you can do, actually, once you understand that notion, then you can extend from these simple hierarchical task networks to an entire programming language. Right? And in some sense, the standard hierarchical task network is a special case of what we call a partial program, which is an arbitrary program in any old programming language. We happen to use Lisp, but you can do this with Java. You can do it with MATLAB if you want. Any language that you can write an agent program in, you can basically leave blanks in that program. You can leave places where you don't know what to do. So you just say, OK, you choose. And then the agent has to figure out by a reinforcement learning process how to fill in those blanks. Each of those choices is going to be made as a function of the physical state and the internal state of the program. So what was just the call stack in a hierarchy, this theta, becomes the entire internal state of the program, which whatever internal memory it has, contents of arrays, the values of arguments, the values of global variables, all of that stuff. So with this, the partial programming languages then do reinforcement learning in that space. And you really can use the full extent of programming languages to write agent programs and still get reinforcement learning to happen in this extended state space. So David Andre did his thesis on ALISP, which was a Lisp version of that, and then Bhaskar Amarthy extended that to concurrent ALISP so that you can actually run lots and lots of agents simultaneously, so you can play strategy games, as we'll see in a minute. And one of the key points about this is that once you look at the reinforcement learning process, what you're learning is basically at each choice that's left open, so each blank that you leave in the partial program, you're going to learn a little Q function, right? A Q function says, for all the possible choices I can make at this point in the program, what's the expected value of making that choice as a function of the state in which I make it. So, so it turns out that this allows a decomposition of the overall value functions that the reinforcement learning system is constructing. And it's somewhat analogous to the way that a Bayes-net decomposes a joint probability distribution into a product of small conditional distributions, each of which depends only on a small number of variables. Right? And this is sort of the key to the entire Bayesian revolution that's happened over the last 25 years. And the same thing can be done with value functions, except it's an additive decomposition of value functions. So let me just give you an example, right? If I'm driving to the airport, this is the subroutine that I'm inside. So in my partial program, there's a drive somewhere subroutine. Within that subroutine, the only things that decisions depend on within that subroutine is basically where you are and things about the traffic. It doesn't depend on the prices of my stocks, right? So the overall agent program may care about getting to the airport because I want to go and have a meeting with my investors to help start my company or whatever it might be. So the whole thing can depend on lots and lots and lots of variables, right? But while I'm driving the airport, the only thing I care about is where I am and is the bridge blocked and stuff like that. So the Q function that makes those decisions is a much lower dimensional Q function than the overall Q function. And the whole Q function is essentially the sum of these individual Q functions that make the decisions at each point in the partial program. So let me just illustrate that. So this is a little snapshot from Stratega. So it's a typical one of these God games where you control everyone and try and achieve some goal. So there's a barracks over there, and so that's the base. There are forests and gold mines, and these are peasants who go and collect resources and bring them back to the base, and then you build barracks and soldiers and have wars against your opponents. And so if I want to write a program for this task, this just to illustrate the idea of partial program, right? So let's start with the lowest level subroutine, navigating to a destination. So here's how you write it. You say, until my position is equal to the destination, I choose a move, which is either north, south, east, west, or stay put. And then I do it. Okay? So that's how you navigate. So that's a partial program, right? Because it doesn't tell the system exactly which direction to go and how that decision depends on the destination. But this choice here will get learned. So we'll set up a queue function to learn this choice. And that queue function will depend, among other things, on the destination, right? And it doesn't take a genius to realize that, you know, when you have a destination, you should move towards it. Okay? Notice that the destination is actually part of the internal state of the agent. There is nothing in the physical environment that tells the agent what its destination is, right? You guys are so used to, you've all learned your MDP theory or your optimal control theory or your whatever, right? Everyone knows that optimal policies in MDPs depend only on the state, right? The physical state that you're in the environment, not on the internal state of the agent, okay? But to describe how an agent should navigate to a destination without mentioning the destination, right, is practically impossible, right? If I'm driving to work in the morning and I get to a traffic light, right, my little internal navigation routine says, okay, when you're driving to work, you know, you turn left at this light. Right? It used to be Oscar's. Coming from the other end, I used to always turn left at Oscar's Burgers. But again, the fact that I'm driving to work is not part of the physical state of the world. So I can't describe that policy without using these internal state variables. Right, so that's a significant change in the way you think about actually learning controllers and designing agent programs. Okay, so just then the rest, right? So to gather wood, basically you choose a forest and then you navigate to that forest. You do a get wood when you get to the forest, and then you go back home and you drop it off. Similarly, to gather gold, you choose a gold mine, you go to the gold mine, you pick up the gold. And then this is the top level, so this will handle multiple peasants. And basically it says, basically you wait for your list of effectors, which are the peasants, to be non-empty. Once your list is non-empty, meaning you have a peasant available, then you set Pez to be the first peasant that's available. And then for that peasant, you choose a task. You either tell the peasant to gather wood, or you tell the peasant to gather gold. But you don't know which one that peasant should do. It's going to depend in very complicated ways on how well you're doing with wood and gold and where all the other peasants are and so on and so forth. So again, we're going to leave that choice to the learning process. So now I'll just show you a learn policy for actually a much more complicated task where you're collecting gold and wood in order to build barracks, in order to build soldiers, in order to send off those soldiers to kill the bad guy. And so we wrote a partial program, a little bit more elaborate than the one I just showed you, and then we left it to run, and in about 2 hours of reinforcement learning, it came up with this policy. Now I'm just showing you the policy being executed. So it starts to build peasants at the base using the resources that the peasants themselves are collecting, and it goes up to so new peasants, so eventually it decides to have 4 peasants, and then once it's got, I think, 3 peasants, it will start to, so now it's got 4, and then it'll start to build a barracks. And it needs the barracks in order to construct the soldiers, so they're starting to build the barracks. Once it has a barracks, it can start to build the soldiers. And Here comes a soldier, almost finished. Oops, that's not a soldier. There should be a soldier. Yeah, okay, that's a soldier. And he waits there, right, because it knows it can't attack the enemy with just one soldier. Now it's got two. They go off and fight the enemy. And the enemy is much bigger than they are, so the enemy actually kills them both. But meanwhile, we're making a third soldier, and we can attack. The enemy's also been wounded, so the third soldier is enough to kill the enemy. Right? So what's interesting about that is that this is 8,550 time steps, and the only reward is the one that comes at the end, which is when you kill the bad guy. And yet it's still able to do reinforcement learning to produce a policy that's fairly successful. In fact, this is about as good as you can get. We couldn't find hand-constructed policy that worked faster than that. Okay. Third topic I've been working on is trying to understand how we can apply these hierarchical ideas to what's called task and motion planning. So in robotics, for those of you who are not in robotics, most of the action selection is about motion planning. Whereas in planning, most of the planning is not about motion, but is about high-level tasks like picking something up, putting something down. So there is no motion planning going on because there is no space, right? There's no X, Y, Z in typical planning systems. They just say, okay, I can pick something up, I can put it in the truck, I can buy something, I can sell something. These are discrete actions that don't have any spatial constraints on them. So these discrete or classical or symbolic planners have now developed to the point where they're pretty effective. So even without the hierarchical stuff that I mentioned before, they can develop plans that are several hundred steps long, and they can do it in a few seconds. But they don't work on continuous processes because essentially the continuous action space is infinite, and the set of facts that you want to write about a geometric domain is also infinite. And so they can't be used for problems involving geometry. So the motion planners are great at dealing with geometry. They have some trouble when you're doing tasks that involve picking things up and putting things down, because those contacts change the dimension of the configuration space and make things much more complicated. There are people who work on these sort of combined configuration spaces where you can make transitions through contacts. But that's quite difficult, and I have trouble understanding exactly how that works. And if you think about a task like laying the table for a dinner party, then you're dealing with probably actually hundreds of objects and thousands of discrete steps. And even if you think about sort of small physical motions, it would be millions of motor control steps if you want to discretize time that way. And so they can't really come up with good plans for that. So what people assumed, and Shaky was really responsible for this. Shaky was the first intelligent mobile robot back in the late 60s, early 70s, is that the task planner will come up with a high-level plan that says which discrete actions that we're going to do. Okay, we're going to pick up this fork, and we're going to go over to the table, put the fork on the table. Okay, we're going to pick up another fork and put it on the table. So the discrete planner comes up with that plan, and then the motion planner figures out how to implement each of those steps, and then we just string it all together. Right? Seems perfectly sensible. Unfortunately, that completely fails. Right? It worked for Shaky only because effectively nothing impeded any of Shaky's actions. So if Shaky said, I'm going to move into that room, I'm going to get the block, I'm going to push it back in the other room, it could always do that. Right? Because there were no obstructions in Shaky's world that could prevent him from doing anything. Whereas, of course, in the real world, you can come up with discrete plans, and then you can try them, and they say they don't work. Oh, because I'm trying to pick up something, but there's something else on top of it. Right? I can try to pick up something, but the gap is too small for my hand to fit through to reach the thing. So these geometric constraints that are not represented in the discrete symbolic representation of the problem, and they can make the actions fail. So the details are a bit unnecessary, but effectively what happens is you start out with a symbolic model of the problem that's optimistic. So it assumes that every discrete action, every pickup, every put down, and so on, can be executed. And then before executing the plan in the real world, you essentially mentally simulate it. At the motion planning level, you find out that some of the motion plans simply can't be constructed. The motion planner reports that it fails, and therefore you learn a new fact about your domain. So you were overly optimistic about your symbolic description. You learn a new fact saying that, oh, from your start state, your attempt to pick up that object failed because there was another object that obstructed that motion. Okay? You add that as a new symbolic fact into the high-level representation, and then you replan, and it will come up with a plan that first of all picks up the obstacle and gets it out the way, and then goes to pick up the thing you wanted to pick up. Okay? And this actually works pretty well, and you can prove that this general approach can be made into a sound and complete planning system that combines, in fact, any task planner. So we can take any old task planner and plug it in, any old motion planner that satisfies certain criteria and plug it in, and put those two together, and they will work. So this was work done with my postdoc Sid, and with Peter Abeel and Lorenzo Riano, and some undergrads as well. So we worked on problems like this, where you're trying to pick up something from the middle of a table with a very large number of objects. We did that was in simulation. We looked at simulations with moving crockery around. We also worked on the actual PR2, so I'll show you the PR2 laying the table. I can see that I'm running over time a bit, but we'll get to the last topic fairly soon. So even though this looks like the kind of thing that you could get a PR2 to do by writing a robot control program, right, and then having motion planning do the individual steps. Point is, there is no robot control program that we have to write. We simply say, lay the table. Right? Here's what we mean by laying the table. The cups have to be in these, everything has to be on the table in this general configuration, and then it figures out everything from there. What you would like to do, which we're not quite ready to do yet, is to say to the robot, okay, go into that person's house, or go into that restaurant, and lay all the tables, right? So it's new crockery, new tables, new storage cupboards, whatever else, and simply have it be able to do that with just a high-level command to do so. Okay. So there's lots and lots of work, endless amounts of work to do to be able to achieve tasks like that. Okay. Last topic, which is going to be done very briefly. How many people have seen this movie? Most of you have. So maybe I should say, who hasn't seen the movie? Okay. It's a good movie, worth seeing, definitely, especially if you're going to work in this area. Without trying to give away too much, so this is one of the robots in the movie. Her name is Ava, and Ava has her own plan. She has her own goals, and this ends up being a little bit of a problem. Right. So, and it illustrates, in fact, her goal is to be at a busy traffic intersection, because I guess she wants to learn more about humanity, and she figures that by being at a busy traffic intersection, she can learn a lot. So that's her goal. Where she got that from, it's completely unclear in the movie, and that's sort of the point, right? So we're building intelligent systems, robots, software, personal agents, you name it, And we're doing it better and better and better, and that all seems great, right? As long as the things you're building have your best interests at heart. Ava has her own best interests at heart, which aren't exactly aligned with everyone else in the movie. So if they're not aligned, that's a problem. And this has been a very popular theme, movies, Age of Ultron, Transcendence, Ex Machina, et cetera, et cetera, et cetera. In fact, Norbert Wiener pointed this out, 1960. Right? So if we use to achieve our purposes a mechanical agency with whose operation we cannot interfere effectively, we better be quite sure that the purpose put into the machine is the purpose which we really desire. Right? And it's fine if what you're talking about is a washing machine. If you had an optimizing washing machine and you didn't put quite the right objective function in, then it's not the end of the world. But if you build systems that are more capable as decision makers than humans are, then it is the end of the world. So we need to figure out how to get these machines to have values aligned with those of humans. And this is really a quite difficult task. So I'll tell you the approach we're taking, which is called cooperative inverse reinforcement learning. You would like to, from this theoretical framework, we would like to understand some pretty basic things, which I don't understand at the moment. So in particular, right, so we're going to have a system that tries to learn the values of humans from observation. And, it's a machine learning problem, so it's never going to be perfect. Right? There'll be things that it doesn't quite understand about human values. Just, like we don't understand each other's values all that well. Right? The fact that we're actually pretty stupid is, intuitively, it seems good. Because even if I don't understand your values perfectly, because I'm not like 1,000,000 times more intelligent than you and vice versa, we can't do too much damage to each other. Right. So, whereas when you have a system that is 1,000,000 times more intelligent than people, right, maybe that little epsilon, that loophole, could still be catastrophic. And so this is the intuition behind a lot of these movies, that that little loophole, that slight difference, misunderstanding, ends up being catastrophic. And I simply don't understand what the right answer is there, but it probably does have an answer. We'd like to understand how computational limitations affect this, and eventually to lay a foundation for what should have been there all along, right? Which is that we want the relationship between machines and humans to be provably beneficial to us. And if you think about it, so sometimes this is called the validation problem. We talk about verification and validation. Verification means you come up with a specification and you show that your machine achieves the specification. Right? Validation is, well, am I happy with the resulting behavior? Right? Or did I make a mistake with the specification? Okay? And that part, validation, is almost unstudied as a problem. All the effort is on verification, is on optimization algorithms, and so on, without actually looking at this other question. Okay, so I think I'll stop there, and you'll have to figure out how we can solve that problem. But we have an approach.
Thank you, Stuart. It's interesting because it's sort of this the Asimovian question, right? Of what are the laws that you can actually verify or validate. I also like the example of the setting the table, because you have a sort of a Towers of Hanoi problem, right? So if it's a sufficiently large number, right, any motion planning problem system will ultimately fail. But if you have that, you need that higher level. One thing about the properties you're talking about is that one common approach to motion planning is sampling, and the challenge there is that you don't get a negative result. What you do need, I think, is that you need to get the system has to be able to tell you that it failed. And a lot of our motion planners don't do that well. Right? They'll just keep going, the resolution complete, but that means that they can run for a very long time until they give you that negative report.
Yeah, so you're right. You can set a bound, and it'll say I can't find within that resolution I can't find it.
Right.
Right. So So our algorithms are complete modulo whatever completeness the motion planner guarantees.
Okay. Yeah. Good. Okay, terrific. So, I mean, what's really nice about this talk and what is implicit also, I think, in the Hami's talk earlier was that the issue right now is really about this kind of formal guarantees, that this is really what is essential. For Hami to be able to do these experiments with kids, he's going to have to prove something that is going to be, some safety margins. And the same thing is what you're after here, is this provably beneficial. I think this is exactly what the initiative is in a great position to do, which is how can we provide those kinds of guarantees. Heuristics aren't enough. We can't just let things that look good and work pretty well most of the time. Is not going to do it in this for the next generation.